Hello viewers, now welcome to another video. Now in this tutorial we'll be learning how to solve this magnetic field question. Now the question reads, a coil of radius 200 millimeters is to produce a field of 0.4 Gauss in its center with a current of 0.25 amperes. Now how many turns must there be in the coil? That is the number of turns, is what we are required to find out. So to be able to calculate the number of turns, now when we know that when current flows through a circular coil, the magnetic lines of induction will emanate, also known as magnetic field lines of force. It will emanate from the center, and then they will form what we call concentric circle around the coil. So which means that now to be able to solve this problem, this question, like I said, when we talk about a coil, now this is what it looks like. A circular coil, this is what it looks like. This is what circular coil looks like. This is what it looks like. So we have the turns of wire around the coil. This is the turns of wire around the coil, because we want to find out how many turns must there be in the coil. So we have the turns of wire. So this is the turns of wire in the coil. This is the turns of wire in the coil. So now, how does the current enters the coil? Now let's say the current enters, from this end, and it leaves here, it leaves the coil on this end. So this is I, and this is also what? I. Now this is the center of the coil. So in this case, so we have the direction, we have the direction. So this will be, so we have, because the current flows in this direction, so this is why the it will be this. So the current in the wire will be taken to be this direction, which is indicated in the diagram. So now let's look at that. So from the center of the coil, is what? Radius. The distance from the center to the what? To the surface or to the circumference is what? Is radius. So that's mathematics. So now, like I said, when current flows through a circular coil, the magnetic lines of induction, also known as magnetic field lines of force, will emerge. They will come out from the center of the coil and form what we call concentric circles around the what? Around the coil, just like what we have here now. We have concentric circle, just like the case of when we talk about the right hand grip rule. When a straight wire carrying conductor or carrying current is grasped with the right hand, with the thumb finger pointing, with the thumb finger along the what? The conductor, the direction of current will point in the direction of the what? Will be in the what? The direction of the thumb finger, while the direction of the magnetic field will be that of the what? Of the coiled finger. Like when we have a straight conductor, this is a straight conductor. Now when a straight conductor is grasped with the right hand, when a straight conductor is grasped with the right hand, like this, so when we have the right hand, when the right hand grabs a straight conductor, so this is the right hand, so when the right hand grabs a straight conductor carrying current, now the direction of current, just like what we have here now, we have a straight conductor, carrying current. That's a straight wire carrying current. Now when the straight wire carrying current is grasped with the right hand, now with the thumb finger along the conductor, and so then the direction of the direction of current, okay, the direction of current will be in the direction of the thumb finger, while the direction of magnetic field, okay, will be in the what direction of the coiled finger. That's according to right hand grip rule. Okay, there are so many ways I can, the law can be stated, okay, and it's still the same way I just explained it now, that when the right hand, okay, grabs a straight conductor carrying current with the thumb finger along the coil, along the conductor. Now the coiled finger, okay, the coiled finger will indicate what? The direction of magnetic field, okay, while the thumb finger represent the direction of current. So this is the direction of current. So that's in the case of right hand grip rule. So all these laws are related, okay, they are related, but because I want to explain the flow of current, that's why I just say, okay, let me talk about this, for us to understand what it means, to when we talk about direction of current and also what direction of magnetic field. When we talk about circular coil, like I said, the direction of magnetic field, okay, depends on the flow of current, through the circular coil. So which means the magnetic field in a circular coil would depend on the flow of current through the coil, and also depend on the number of turns. Okay, that's, like I said, this is what we call the turns of wire, but we have the direction of the magnetic field. Okay, so then apart from that, then it also depends on what we call it also depends on the radius. Okay, that is a distance from the center. Okay, that's the distance from the center of the coil. So that's in the case of, so this is just to explain right hand grip rule. But in the case of a circular coil, yes, like I said, we can use the Faraday's experiment. But what we need in this case, in order to solve this problem, is now we know that the magnetic field of a circular coil depends on number of turns. Okay, the magnetic field of a circular coil also depends on the current, okay, the current flowing through the coil. At the same time, it also depends on the radius, okay, that's the distance from the center of the coil. All right, so when these are combined, okay, we also have now, so we have here that B is proportional to Ni over R. Okay, so the constant in this case that we're going to introduce, so we have B to be equals to permeability of free space multiplied by N multiplied by the current through the coil over, so this will be permeability of free space, 1/2 of permeability of free space, then multiplied by radius, okay, radius of the coil. Okay, so in this case we want to find we want to find how many turns must there be in the coil. So which means we need to express N in terms of magnetic field strength, okay, then the current flowing through the coil and every other parameter. So we have N to be equal to 2BR over then the permeability of free space multiplied by current I. So this is the formula we're going to use to calculate number of turns. Now let's now identify the given values. So we have the radius. Okay, the given values are, so we are given radius R. Okay, radius is 200 millimeters. That's 200 millimeters. So the radius can now be 200 times 10 raised to the power of -3 meters. That's the radius. Okay, then the magnetic field. Now we're giving the magnetic field to be 0.4 Gauss. So we need to convert this to Tesla. Now please, it should be noted that 1 Tesla is 10,000 Gauss. Okay, 10,000 Gauss. So which means in this case, to be able to convert this to Tesla, so we're going to have B to be equals to 0.4 multiplied by 10 raised to the power of -4. So the unit now becomes Tesla. The unit will become Tesla. Okay, so we're also given the current entering the coil. So the current entering the coil is 0.25 amperes. Now we want to calculate the number of turns. So having identified the given parameters, that's a given value, Now, the only one that is missing is the number of turns. So to calculate the number of turns, so we're going to make use of this formula. Okay, we're going to make use of the formula N equals to 2BR over permeability of free space, okay, multiplied by what? Current I. Now, don't forget that the value of permeability of free space is 4 pi times 10 raised to the power of -7 Henry per meters. Henry per meter. So now let's now use that to get the value of N. So we have N to be equals to 2BR over permeability of free space multiplied by I. So we have N to be equals to 2 multiplied by 4 times 10, okay, raised to the power of -5, okay, then multiply by the radius, which will be, so when we multiply 200 by 10 raised to the power of -3, that will be 0.2. That's same thing as 2 times 10 raised to the power of -1. So the value of permeability of free space is 4 pi times 10 raised to the power of -7, then multiply by the value of current, which is 0.25. Now, remember, number of turns has no unit because it is a dimensionless quantity. So let's get the value for N. Now, we know here that 2 times 4, that's 8. 8 times 2, that will be 16. So we have N to be equals to 16 multiplied by 10 raised to the power of -6. Now, 0.25 multiplied by 4, that will be 1. So here we have pi. Pi multiplied by 10 raised to the power of -7. So this will be 3.142 times 10 raised to the power of -7. So what is 16 divided by 3.142? That will be 5.09. So this will be, we have N to be equals to 5.09, okay, then multiply by 10 raised to the power of -6. So I'm going to add this power to this. So that will be -6 plus 7. So that will be N equals to 5.09 multiplied by 10 raised to the power of 1. So multiplying 5.09 by 10, that will be 50, okay? So, or 50 point, that's 51. So we have the number of turns to be 50.9. And we can approximate that to be, it will be approximately 51. So the number of turns is 51. Okay, so like I said, coil, okay, we can relate all the rules, you know, in electromagnetism. They are all related. You know, we know the goal, okay, is to what? Is to find out the magnitude and direction of magnetic field, all right, in a coil, in a solenoid, in a toroid, and many others, okay. So in this case, you know, like another way this can be explained, we can use the Faraday's experiment. You know, the case of when we have in the North Pole, for instance, when the North Pole of a bar magnet, okay, is pushed, you know, towards a coil, that's a stationary conducting loop. Now, a current will be induced in the coil. Okay, just like what I explained about this, that's when current flows through a coil, okay, the flow of current will bring about, that is, it will generate what we call magnetic field. Okay, so the magnetic field lines of induction or the magnetic field lines of force will now emanate from the center of the coil. Okay, now when the direction is clockwise, okay, when the direction of current is clockwise, the magnetic field lines of induction, okay, will emanate from the center and it will be in the downward direction. Okay, but when it is anti-clockwise, then the magnetic field lines of force will also emanate from the center, but it will be in the what? In the clockwise direction. Okay, because when current is clockwise, the direction of magnetic field lines of force will be what? Will be anti-clockwise. Okay, it will be downward rather. Okay, so when it is anti-clockwise, that's when the flow of current is anti-clockwise, then the magnetic field lines of force, okay, will be what? They will emerge from the center of the coil upward. That is in the upward direction. In the upward direction. So this is how to understand the magnetic field of a coil. You know, when I said when current flows through a circular coil, okay, a magnetic field will be what? Will be generated or created, okay? And the magnetic field lines of induction, okay, will emanate from the center, okay? Just like the case of when the north pole of the bar magnet, in this case, is pushed towards the stationary conducting loop. And like I said, a current will be induced. This is the induced current. So this induced current will be will flow in a particular direction, and this is the direction. So the direction of the induced current, okay, like I said, the direction of magnetic field depends on the direction of induced current, okay, of the current flowing through the coil. So, and in this case, when it is pushed to the right, I mean the bar magnet, okay, the lines of induction of the magnetic field, okay, which is when the induced current is, that's when current is induced, they will come from the left, that's from the right, okay, in order to counteract the increasing magnetic flux, okay, from the what to the what to the left. But in the when the north pole of the magnet is now pushed away from the coil, when it is pushed away, okay, from the coil, okay, so in that case, when it is pushed away from the stationary coil, now the induced current, okay, will produce its own magnetic flux in order to counteract the decreasing external magnetic flux to the what to the left. And this is one of the ways to explain the magnetic field of a circular coil when it comes to the Faraday's experiment. We also have some other laws like the Amperes law, the Lenz law, the Lorentz, and the rest of them. For the question, we got N to be equals to 51, and that is the number of tons. That's when approximated. Then don't forget that I said 1 Tesla is equals to 10,000 Gauss. The noblest pleasure is the joy of understanding. Bye-bye.